Okay, so this is a great little example here. What we have is a mechanism made up of links OA and BC, and we're told that links OA and BC are pinned to ground at points O and C respectively, and that pin A of link OA is able to slide within a slot that is cut in link BC as shown. We're told that pins O and C are on the same horizontal line, and that the little XYZ axes are attached to link BC. Pardon me, at the instance shown, we're told that link BC is vertical with a given value of L, and that link BC is rotating counterclockwise at a rate of given by omega. And based on this information, we're asked to determine the angular velocity of link OA, as well as a value for L dot, the rate of change of this quantity L. Okay, so in this case, we already have a rotating frame set here. We have the little x and y axes defined, and I'm going to go ahead and set up a second global set of axes, which will be effects to ground, and I'll call those capital X and capital Y respectively. And I'll simply note here that if we wanted to find, for example, the distance between OC, we could do so. And for this problem, I'm simply going to call it D. And note that D could be equal to, in this case, the square root of the 0.5 meters quantity squared minus L squared. And so you could plug in the numerical value for L given in this problem and recover D at any point in time. Alright, with that in mind, let's go ahead and see how we could find the velocity of point A using two different relationships and see if that helps us out, which in this case I'm going to assure you it will. So the way I'm going to do that is I'm going to first of all note that link AO is a rigid body and that points A and O lay on the same rigid body, and given that piece of information, I can say that the velocity of point A is equal to the velocity of point O plus the angular velocity of link OA crossed with the position vector of A with respect to O. If I do some substitution here, I'm going to have 0 plus omega OA in the little k direction, the capital K direction, crossed with R of A with respect to O, which is going to be a distance of, in this case, D in the capital I, plus L in the capital J. And so if I go ahead now and substitute this in, I'm going to have K cross I is going to give me a J, so I'm going to have D times omega OA in the capital J, and K cross J gives me a minus I, so I have minus omega OA times L in the I direction. Once I have that in place, I can also define the velocity of A using the rotating reference frame, referenced in this case to this point here at the bottom, point C. So specifically, I could say the velocity of point A is equal to the velocity of point C plus the velocity of A with respect to C, as seen by the observer, plus in this case the omega of the rotating frame, cross the position vector of A with respect to C. So if I do some substitution here, I know the velocity of point C is 0. The velocity of A with respect to C is simply going to be L dot, and that's going to be in the little j direction. And then I can add to that omega, which in this case is going to be omega BC in the little k, and I can cross that of R of A with respect to C, which will be a distance L in the little j. If I go ahead and expand this out here, I'm going to have L dot in the little j, plus k cross little j is going to give me minus little I, so I'll have minus omega BC times L in the little I. Now at this juncture, what I can note is that the capital and little axes are aligned at this instant in time. And so in this regard, I can go ahead and look for the answer. If I look and say at the little I direction, which of course is the same as the capital I, and I equate the two expressions for VA that I've developed before, namely this one right here and this one right here, I'll get the following result. I'm going to get from here minus omega OA times L is equal to minus omega BC times L. And from this, I can get a numerical value for omega OA, namely that omega OA has to equal omega BC. And in this case, if I want to write these in vector form, what I'm going to find is that it's actually equal to, in this case, omega BC, and in this case, the little k direction. I could write that in capital K2 if you'd like. If I look at the j components, I'm going to have D times omega OA is equal to L dot. And so that'll give me a numerical value for L dot, the other quantity I'm asked to find. Alright, from here on out, it's just straightforward plug and chug. You can plug in the numbers given in the problem and get an answer. I know you can do it. Best of luck.